Grüezi! Today we're going to set you up with everything you need to start creating your own effects for the Polyend Endless. There are three things we'll require for this. First, the ARM GNU toolchain. This is a set of tools that helps us compile our code for the Endless hardware. We specifically want to use the ARM non-EABI version of it, where ARM specifies the system architecture, as in the instruction set the CPU uses. Non means there is no underlying operating system, so the code runs bare metal. And EABI stands for Embedded Application Binary Interface, which defines the standard conventions for how the compiled code interacts with the hardware. Second, we'll want an IDE, or Integrated Development Environment, like Visual Studio Code. In this case, we're going to use CLion by JetBrains. Mostly because JetBrains IDEs are my go-to, it's not Microsoft, and they are also available for free for non-commercial use. And third but not last, the FX Patch SDK, our software development kit provided by Polyend on GitHub, which will give us a basis to write our own effects for the pedal. With that out of the way, the video has chapters with setup instructions for Mac, Windows, and Linux. You can also find the timestamps in the video description, as well as all the links you'll need for the downloads we require. Once we're done with the setup, we'll have a quick overview of the SDK so that you'll be ready to go after this video. Let's download the ARM GNU toolchain. Make sure to grab the version specific to your CPU. If you're on a newer Mac like me, you'll want the Apple Silicon version. Search the page for Mac OS and download the ARM non-EABI tarball. Next, download and install CLion. You can grab the disk image or use the JetBrains tool app if you want to easily handle updates in the future. Finally, download the FX Patch SDK from the Polyend GitHub repository. Go to the Code button and select Download Zip. Before we launch CLion and set up the project, let's prepare our files. Extract the SDK. Inside the extracted folder, you'll notice a VS Code folder in case you want to use Visual Studio Code later instead. Next, extract the ARM GNU toolchain. Once finished, I'll rename that folder to AGT15-2. I'm also going to rename the SDK folder to Example, but you can name it anything you want or leave it as it is. Feel free to move these folders to your preferred destination to keep things organized. On your Mac, you may not have make installed yet. You can check by opening up the terminal and running xcode-select-install. Now that we have all the pieces, let's launch CLion. Select Open and navigate to the example folder we just prepared. Once the IDE has opened, a dialog will appear asking you to clean the project. We can ignore this for now, so click Cancel. First, let's configure the toolchain. Go to Settings, navigate to Build, Execution, Deployment, Toolchains. Click the plus sign and choose System. Let's name the toolchain AGT15.2, based on the available version when making this video. Now choose the C compiler binary. Click the folder icon and navigate to the bin folder inside your ARM GNU toolchain directory. Look for the file ending in -gcc. Repeat this for the C++ compiler, choosing the file ending in -g++. And do this one more time for the debugger, selecting the file ending in -gdb. Before you close this, highlight the path to one of these binaries and copy it to your clipboard. Then hit Apply. Now let's set up Makefile. In the Makefile settings, select the AGT15.2 toolchain. In Arguments, type toolchain equal, all caps, and paste your path. If you lost the path, you can right-click the file in Finder, hold the Option key, and select Copy as Path Name. Remove the file suffix so the path ends at ARM non-EABI-. Click OK. Now that we have all the settings in place, let's open the Makefile itself from the project tree on the left. Scroll down until you see a green play icon in the gutter next to the first build target on the left. Click it. The compilation will fail for now, but this adds the configuration to the Run menu at the top right for easy access later. Scroll further down and do the same for the clean command. To make future builds work, go to Edit Configurations at the top right. Select the All target and in the Environment Variables field, add toolchain equals, followed by the same path we used before, ending in arm_non-eabi-. Hit Apply and OK. If you open patchimpl.cpp, you might notice the syntax highlighting isn't fully active yet. To fix this, simply close and reopen the project. The clean dialog will appear again. This time, click OK. After a few seconds of indexing, highlighting will work correctly. When you run all from the top right, a build folder will be created now containing your compiled effect as a .endl binary. And that's it. You're ready to develop your own effects. First, let's download the ARM GNU toolchain. On Windows, you'll likely want the x86_64 version. Search the site for Windows and download the arm_non-eabi zip file. Next, you should download and install CLion. Either download the executable, or you could also use the Toolbox app if you want to update easily in the future. We also need msys2 to provide the make utility. Download the x86_64 installer. Finally, download the FX Patch SDK from the Polyend GitHub repository. Go to the Code button and select Download Zip. Before we launch CLion and set up the project, let's prepare our files. Extract the SDK, and if you want to, rename the extracted folder to Example. You can name it anything you want or leave it as it is. Inside the extracted folder, you can see there's also a VS Code folder, in case you want to use Visual Studio Code later instead. We also have to extract the ARM GNU toolchain, and this will take a moment. Once that is done, rename it to AGT15-2. Move these folders where you can easily find them later. Run the msys2 installer and follow the prompts. Once finished, ensure Run msys2 now is checked, then click Finish. We need to install the build tool make by typing the following command in the msys2 terminal. You can also find all of this ready to be copy-pasted in a written tutorial. The link is in the video description. Press Y and Enter to proceed. Once the installation is complete, you can type Exit to close the shell. Now that we have all the pieces, let's launch CLion. Select Open and navigate to the example folder we just prepared. Once the IDE has opened, a dialog will appear asking you to clean the project. We can ignore this for now, so click Cancel. A notification may also appear regarding Microsoft Defender. Click Exclude Folders to ensure the real-time protection doesn't slow down your builds. Let's configure the toolchain. Go to Settings, Build Execution Deployment, Build Tools, Make. Click the folder icon for the Make executable, navigate to your Windows drive, usually C, and go to msys64, ucrt64, bin. Select the mingw32-make executable and hit Apply. Now let's go to the toolchains and add a new system entry for the ARM GNU toolchain. Let's name it AGT15.2 because that's the current version as of the making of this video. Choose the C compiler binary. Click the folder icon and navigate to the bin folder inside your ARM GNU toolchain directory. Look for the file ending in -gcc. Repeat this for the C++ compiler, choosing the file ending in -g++. Do this one more time for the debugger, selecting the file ending in -gdb. Before you close this, highlight the path to one of these binaries and copy it to your clipboard. Then hit Apply. Last but not least, let's set up Makefile. In the Makefile settings, select the AGT15.2 toolchain. In the arguments, type toolchain equals, all caps, and paste your path. Remove the file suffix so that the path ends at arm_non-eabi-. Click OK. Now that we have all the settings in place, let's open up the Makefile itself. from the project tree on the left. Scroll down until you see a green play icon in the gutter next to the first build target on the left. Click it. The compilation will fail for now, but this adds the configuration to the Run menu at the top right for easy access later. Scroll further down and do the same for the clean command. To make future builds work, go to Edit Configurations at the top right. Select the All target, and in the Environment Variables field, add toolchain equals, all caps again, followed by that same path we used before, ending in arm non-EABI dash. Hit Apply and/or OK. If you open patch-impl.cpp, you might notice the syntax highlighting isn't fully active yet. To fix this, simply close and reopen the project. The clean dialog will appear again, and this time, click OK. After a few seconds of indexing, highlighting will work correctly. When you run all from the top right, a build folder will be created now containing your compiled effect as a .endl binary. And that's it. You're ready to develop your own effects. In my case, I'm running Arch, by the way, but this should be pretty straightforward for all Linux users. Let's get started and download the ARM GNU toolchain. We need the x86_64_Linux version. The easiest way to find it is to search the site for it, and make sure to download the ARM non-EABI tarball. Next, download and install CLion from JetBrains. Depending on your distro, you can download the tarball or use the Toolbox app to handle future updates easily. Finally, download the FX Patch SDK from the Polyend GitHub repository. Go to the Code button and select Download Zip. Before we launch CLion, let's organize our files. Extract the SDK. Inside the extracted folder, you'll also see a VS Code folder in case you prefer using Visual Studio Code. I'm going to rename the SDK folder to Example, but feel free to name it whatever you like. Next, extract the ARM GNU toolchain. This will take a moment. Once it's finished, I'll rename the folder to AGT15-2. You can move these two folders anywhere you like to keep your workspace organized. Now that we have all the pieces, let's launch CLion. Select Open and navigate to the example folder we just prepared. Once the IDE has opened, a dialog will appear asking you to clean the project. We can ignore this for now, so click Cancel. First, let's configure the toolchain. Go to Settings, navigate to Build Execution Deployment, Toolchains, click the plus sign and choose System. Let's name the toolchain AGT15.2, based on the available version when making this video. Now choose the C compiler binary. Click the folder icon and navigate to the bin folder inside your ARM GNU toolchain directory. Look for the file ending in -gcc. Repeat this for the C++ compiler, choosing the file ending in -g++. Do this one more time for the debugger, selecting the file ending in -gdb. Before you close this, highlight the path to one of these binaries and copy it to your clipboard. Then hit Apply. Next, let's set up the makefile. Go to the makefile section in Settings. Set the toolchain to the AGT15.2 entry we just created. In the Arguments section, we need to add a toolchain argument. Type toolchain equals, in all caps, and paste the path you copied. Remove the file name ending at the end so the path stops at ARM non-EABI dash. This tells the makefile which compiler prefix to use. Click OK. Now that we have all the settings in place, let's open up the makefile itself from the project tree on the left. Scroll down until you see a green play icon in the gutter next to the first build target on the left. Click it. The compilation will fail for now, but this adds the configuration to the Run menu at the top right for easy access later. Scroll further down and do the same for the clean command. To make future builds work, go to Edit Configurations at the top right, select the All target, and in the Environment Variables field, add toolchain equals, followed by the same path we used before, ending in ARM non-EABI dash. Hit Apply and/or OK. If you open patchimpl.cpp, you might notice the syntax highlighting isn't fully active yet. To fix this, simply close and reopen the project. The clean dialog will appear again, and this time, click OK. After a few seconds of indexing, highlighting will work correctly. When you run all from the top right, a build folder will be created now containing your compiled effect as a .endl binary. And that's it. You're ready to develop your own effects. Now that we have a working development setup, let's have a look at the SDK and its structure. Let's look at the patch header file, patch.h, so we get an overview of what we are working with. First, let's look at the available enumerators. Param ID are the IDs for the three knobs on the Endless pedal. Action ID defines the available actions for the left foot switch. The one action that is currently missing here, that I'll hope we'll get soon, is a K left foot switch released. It's very likely this will be added or might already be available by the time you are watching this video. I'll make sure to put any up-to-date information in the first pinned comment of this video. Next, there are two constants that allow you to define some defaults for your effect. K working buffer size allows you to set the size of the audio buffer you want to work with. Specifically, you have about 50 seconds worth of mono or around 25 seconds worth of stereo data to work with, or around 2.4 million floats at max. K sample rate defines the sample rate you want to work with 48K being the maximum. Parameter metadata is a struct defining the min-max and default values for knobs. And then we got some more enumerators. Param source will tell us if the source of a parameter change was from the knobs or from the expression input on the side of the pedal. And color defines all available LED colors that we can use to give visual feedback to users. Next are the exposed methods that are available to us. The init method, as the name implies, is for the initialization of your effect. Use this to set up any variables or states that your effect will require. SetWorking buffer is aptly named as the method where you will receive the available memory buffer. This method is called once, so take the buffer and store it in a variable so you can continue working with it. The buffer is useful for delay lines, loopers, reverb or tails, and granular applications. Keep in mind that the buffer is a flat array of floats, so in order to handle stereo data, the standard approach would be to interlace or interleave the data, meaning you would alternate between left and right samples for every index that you add. Process audio is the actual workhorse and core of the engine that runs continuously at a very high rate. This is where you want to do all your audio processing. In this method, you receive two flat arrays, one for the left audio channel input and one for the right. Finally, let's deal with the physical aspect of things. Get parameter metadata allows you to define the min-max and default values per knob. Set param value is the event handler for when the user actually twists a knob on the device, and will allow you to update your variables with whatever value you receive. And to complete the knob trifecta, isParam enabled is a way to define if a knob or the expression input is enabled or not for your effect. Handle action is the event handler for when the left foot switch is either held or pressed, and as mentioned earlier, hopefully by the time you watch this video, we will also have a way to handle the switch release. Last but not least, we have getStateLED color, which is a method that is periodically called to update the state of the LED on the device. You can use it to update the LED color and give the user visual feedback on things that are happening. Let's actually use the LEDs to write a quick code example and do a deployment to the pedal. Alright, so I'm going to open up my patchimpl.cpp, and it's going to be different from the one that you received from the SDK, because the one in the SDK is a big crusher example, and I don't need all that stuff. I just want to make a simple example with LEDs. So SetWorking buffer doesn't do anything, process audio just receives the audio and puts it right back out, and everything else is pretty much empty, as simple as it gets. So if I want to change the LED if a user twists a knob, for example, I would start by creating a variable called, I'm just going to call it PLED, and I'm going to call the initial state to be white. And then in order for us to always see the color that we defined here, we need to update getStateLEDColor. So I'm just going to return PLED in here. And so if a user changes a parameter on one of the knobs, I want to actually do something with it. So I'm just going to use a switch case with the ID of the knob. And as we've seen in patch H, and as we see the param ID, the left one would be obviously 0, the middle one would be 1, and the right one would be 2. So we're just going to add some cases here. Case 0, set PLED to, let's do RGB colors. So let's start with red. And then we want a case 1. I don't want it blue, I want it green. Let's go with dim green. And then we have the third case, RG, well, which will be blue, of course. As you've noticed with C-line, you get predictable line completion. So I didn't have to write all of this, which is quite nice and quite fast. But I'm going to add a break here, just so we have that as well. And that should be it. I define a variable PLED, which starts in white. I pass it to this function getStateLEDColor, and I override it whenever someone handles or changes something on one of the knobs. So all that is left to do now is to compile this, which means we get a build folder and we have our .endl for endless patch binary file that we can now deploy to the pedal. And in order to do this, I'm going to have to switch to my overhead camera. So let me scoot over to that desk real quick. Here we are. And I'm gonna go into the build folder here where this file is. And you notice that the Endless already has shown up as a removable drive because it's connected via USB-C. So all I have to do is grab this file and drop it into the Endless. And what is going to happen is that it's going to go yellow, which means it's deploying it. And once it is done, it's going to power cycle, which means the Endless disappears over here. And once it's back up or booted, it should flash with green LEDs, as we see here. And the initial state now is white as expected. So as soon as I turn my knobs now, we have red, we have green, we have blue. So as you see, it works as it should. Now let's go back to the code real quick. Where's my mouse? There it is. Another nice thing that we can do now is, for example, with the handle action, we could listen for the press of the left foot switch, and we could build a toggle so we could have more parameters that we can control. So I'm just going to add a Boolean here, and I'm going to call it pState, and initially it's false. And whenever you press the left foot switch, I'm not even going to differentiate here between if it was held or just pressed. I'm going to switch the state, which means I don't really need this variable here. And with that, I could implement more parameters. So I could say pState, and then I would like to have a different color. So what color do we want to use? Let's say I want to use dark cobalt here. And I want to use I don't know, let's go with magenta. And last but not least, let's go with dark lime for this. So once we have that, I'm just gonna compile again. As you see now, we also get a new binary file here because they use a timestamp. So you should always have the newest on the bottom. And now let me scoot over to my desk again. Where's my mouse? There it is. And as you see here, we have now the new file. So I'm going to do the same thing. I'm just going to drag it over again. And it's deploying again, showing yellow. Will power cycle. And there we go. Now we're back in the normal state where we have RGB. And if I press the button, now we see the other colors as well. And if we go back, we have the first set of colors. So this way you could easily have more than those 3 knobs. So you can have multiple variables, or as many as you want technically, to handle all those different states that you possibly would want to have. Another thing I want to show real quick is how to update the firmware of the device. And for that, I'm just going to disconnect it now. And I'm going to have to reconnect it actually. That was a really big mistake from me. I have the 1.0 firmware here. So since I have to reconnect it, I'll do that. But I'm going to have to unplug the power. I'm going to use this little thing here because on the Endless there is a little reset button up here. Don't mind this connector. This is a pre-build, pre-production build, so it's going to look different on your device. So I'm just going to take this and press the power button in. Did I get it? Yes, now I got it. And I'm going to plug the device back in. And it's going to blink. And I need to plug the USB back in because this cable doesn't stick very well. There we go. The Endless shows back up, but it now shows FWU for firmware updates. So when you grab the firmware, you can just place it inside. It's going to blink. Go green. And then start again, and then the regular drive shows up again. So at this point you can continue working on it or adding other effects if you want. And that's pretty much it. I hope this is helpful. If you got any questions, feel free to leave a comment or go to the written tutorial on Backstage and leave a comment there. I'll gladly help as far as I can. And yeah, see you around. Bye.